Thank you very much for the introduction, and I'm grateful to the organizers for inviting me here and for the opportunity to give a talk. I'll speak about higher braided categories. So the main idea that I'd like to convey today is that how, some problems in the theory of usual braided categories lead to higher braided categories. I would try to avoid technicalities. My intention is to present like a general idea, describe the problems people are thinking about and how they naturally lead to higher categorical structures. Now, such a passage from, categories to higher categories is not surprising because that's what happens in algebra and representation theory. When you study rings, you are naturally led to study of modules over them. When you study Hopf, which are abelian categories, when you see Hopf algebras, you are naturally led to their representation categories, which are tensor categories, and that sheds the light on the objects we study. Okay? So please, I will be happy to answer any questions as they arise. So if you want me to slow down or speed up, just tell me to do so, okay? Any questions so far? Good. All right. So I'll start then. So the notion of a tensor category appeared yesterday, in particular in Alexei Davidov's talk. The tensor category C is an abelian C linear. Let's say we are going to work over complex numbers today. Category. So here, abelian means that you can do linear algebra. You can talk about kernels. Kernels, C linear means that home spaces are vector spaces, along with the tensor product bifunctor. Yes, you can take direct sums, right? Morphisms have kernels and k-kernels. Think about representations of an algebra, okay? So whatever you can do with representations of an algebra, you can do in abelian category. That's enough for the purposes of this talk. So C-linear category along with a bifunctor. Also, I'd like to make sure that people don't break their eyes. So if the letters are small or illegible, let me know, okay? So along with the tensor product bifunctor and associativity constraint. Which so that, a pair of triple products of objects is associative, but we care about the way in which it is associative. Now, these constraints are to satisfy additional compatibility, namely there is a pentagon diagram that is to be satisfied. Alexei presented this yesterday in his talk. Now, a braiding is an additional structure. On C is additional structure, and I don't think such categories appeared early in this conference. So, well, if this is an associativity constraint, then braiding is a commutativity constraint. So you have a collection of morphisms like this for all objects in the category, so that objects commute, but again, they commute in a certain controlled way. And these constraints, so commutativity, that's right, yes, of course. commutativity constraints, they are to satisfy their own axioms, which are called hexagon axioms. It's very easy to explain what they are. You see, like if you permute an object with a pair, this can be done in two ways, right? You permute it with a pair at once, or you can permute it with a pair with each factor separately. So let me write this down. So if you have X tensor, Y tensor Z, so our goal is to permute this product of X and Y with Z, right? Okay, so this can be done. You know what, no, instead I would permute X with Y and Z. So what we can do first is to permute X and Y. This would take us to Y tensor X tensor Z. Then we can apply associativity. And shift the brackets. And then we can permute X with Z. But you see, the same can be accomplished in a different way. So what we did here, we permuted X with Y and then X with Z. Now, instead, let's permute it with the product. Okay, to do so, well, we need first to apply associativity so that Y and Z come together. So it would be X, tensor Y, tensor Z, the associativity constraint. And so now we have Cx Y tensor Z, permuting X with the product. So it would be Y tensor Z tensor X. And then we apply associativity constraint again to get there, right? So this is called appropriately a hexagon axiom. Now there is a kind of symmetric version of this when you permute, the object you permute with is not on the left, but on the right, okay? You can figure out what that would be. So here X is on the left. You permute it with two objects on the right, yes? So, you know, you can interpret this as a sort of a bilinear condition. So X, Y, Z is B, X, Y, B, X, Z. A special case of a braiding would be given by a bilinear form, yes? Now, bilinear form has two conditions. It's linearity with respect to the second argument and linearity with respect to the first. So that's what I'm trying to say. Make sense? Plus analogous hexagon. Okay, so these are braided categories. Now, well, from the definition I gave, it appears that a braided category. So what I'm trying is to, well, this will also come later, but a good analogy to keep in mind with this braiding is a bilinear form. So this condition, yeah. So, okay, so here is what I'm trying to do. Like if you look at the instances of the braiding here, so if you look at the appearances of the braiding here, right, CXY, CXZ, and CXY tensor Z, right? It does resemble the bilinear form condition, the linearity with respect to the second argument. You can draw a similar diagram that is analogous to linearity with respect to the first argument. That's my point. Okay. So, okay, so from what I said, formally, braided category is a tensor category with an additional structure. Okay. Now, formally, this is correct, but this is not right. Okay, it's not right to think about it this way. This is how, you know, for instance, when we study abelian groups, we do not study them as a special case of a non-abelian group, right? There is a separate theory. And commutative algebra is a separate, you know, subject from non-commutative algebra. It uses different ideas. I'll try to show them, okay? Mm-hmm. All right, so, yeah, examples, yeah. So, Again? Oh, yeah, okay. I'll push it all the way up. Okay, yeah, like this. Is it better? Oh, okay, I see. It would be hard for me too to jump and write. Yeah, okay, sure. So yes, now examples do appear, so informally speaking, examples of such things appear each time when you have a structure such that you can tensor objects in some inconsistent way, and this procedure is somehow naturally commutative. So, right, the basic examples that you already mentioned would be representations of groups, representations of Lie algebras, and more generally are representations of quasi-triangular Hopf algebras, of which, of course, quantum groups is a special case, right? No, well, okay. So this is a good point. The problem is that some categories may have more than one braidings. Some may have none. Okay. So in principle, of course, when you talk about the representations of a group, then there is kind of a natural symmetric braiding, right? And it's not very interesting. Well, there are other braidings on the same category. Okay, but what is true, of course, is the most interesting categories, they have braidings which are somehow non-trivial, and I'll try to quantify that, okay, later on. So, yes, so there is a powerful construction called the Greenfield Center, or double of a tensor category. So now, here is a tensor category, is an ordinary tensor category on which there is no braiding. So let's give it a name, let's call it C. So then the center of C would consist, the objects of the center would be all pairs Z gamma, whereas Z is an object of C, and gamma is a natural family of isomorphisms like this. It permutes an object in the category with this given Z. Okay? Now, it should be clear why it's called the center, right? Because that's the condition that Z commutes with objects. Again, in the spirit of this theory, we record the way in which these objects are permuted. Okay? Now, this structure allows in particular to permute like two different Z's. So such a category naturally becomes a braided tensor category. Again, if you've ever seen like things like Greenfield double, that's that. That's precisely this construction. Another example, which is perhaps the most basic, but in a sense, kind of very suggestive, is the following. So, given an abelian group A and the quadratic form Q on A with values in the multiplicative group of the field. So one can define, one defines a braided category, which maybe I'll continue here. Oh, I'll give it a name here. So I'll call it like the CAQ. So as a tensor category, this is the category of A-graded vector spaces. A-graded vector spaces as tensor category. And then the braiding on it, well, it's a vector space along with the decomposition into the direct sum of subspaces labeled by A. Yeah. Okay, so now it's very easy to describe what are simple objects in this category, right? So these are like one-dimensional vector spaces which are supported on a particular element of a group. So the braiding in this category is determined by this. So if so let I want a name for it. So let's say XA, where A and A be simple objects of this category. Then the braiding satisfies this condition. So the braiding of this object with itself is given by this quadratic form. So conversely, any category that has this property, let's say it's semi-simple and every simple object is invertible, would determine a quadratic form by taking a self-braiding of a simple object with itself. Okay, so this goes back to the work of Joyal and Street from the 1980s. But the important, and again, it's rather elementary, but what's important is that it brings a kind of linear algebra insight into this, okay? So because you see, like whenever there is a quadratic form, one can think about things like orthogonal complement, for instance, right? Isotropic subspace and so forth, right? So, and this is very important. So this brings, yes, well, okay, so what it does determine is an equivalence class of a category. Quadratic form determines in particular bilinear form, right? Now, this bilinear form is somehow the square of the braiding, yes? So let's pretend that this quadratic form is a diagonal, like of a bilinear form. Then it does, that's like the thing that we discussed earlier with you when I brought like this condition, right? About bilinear form. So here a bilinear form naturally corresponds to a braiding. Yes, so there is some work involved that show that this in fact determines the other braidings as well, up to equivalence of categories. So this brings a geometric insight as follows. I'll give the following definition, which is due originally to Michael Mueger. So we say that two objects, X and Y of C, centralize each other. So here a C is a braided category. If the squared braiding between them, you see the braiding can be composed with itself. So we can braid X and Y, and then we can braid Y and X. And in principle, this doesn't have to be identity, right? It is identity if a category is symmetric, like in these boring cases. For like representations of quantum groups or Greenfield centers, that's very far from that, okay? So we'll say that if these two things do centralize each other, if in this case the squared braiding is identity, okay? So in particular, given a subcategory, let's say D of C, subcategory, one can introduce an analog of the orthogonal complement, take D prime, to be a subcategory consisting of all, Y are in C, with the condition that all these Y's centralize objects of D. Again, if you keep in mind this example with a quadratic form, that is precisely the orthogonal subspace given to the corresponding to a subspace, right? So this is called the centralizer, and it's an analog of orthogonal complement. Okay, so now this allows, in particular, to quantify, this thing about braiding being trivial or non-trivial, right? So a category C is symmetric if it's, of course, coincides with its own centralizer. This is the same as to say that any two objects centralize each other, right? Think about the trivial quadratic form. And C is non-degenerate. If the centralizer of C, the radical, so to say, is trivial, right? Because there always will be objects that centralize each other, namely the multiples of the identity object, the trivial object, right? The trivial representation would centralize everything. So if this is just the category of vector spaces. Make sense? So this is as small as possible, a trivial subcategory. So, and these are the categories that people love most because they lead to the most interesting applications, okay? So in particular, the Greenfield Center of a here that I defined here. The Greenfield Center of a tensor category is non-degenerate. Now, there are many reasons why non-degenerate categories are important. Incidentally, they are, sometimes you would see the name modular category. That's almost the same, okay? It's in the presence of a ribbon structure, non-degenerate and modular are identical notions. Okay, now the reasons people are interested in non-degenerate or modular categories is that in particular in low-dimensional topology, they lead to all this invariance of knots and manifolds. People construct topological quantum field theories from non-degenerate categories and so on. Now, in physics, such categories are used to model topological faces of matter. So somehow it's very important that this model involves non-degeneracy. Right? Any questions? Right? Now, there is of course, there is this subcategory called the symmetric or Mueger center of C that controls how far this category away from a non-degenerate one. So these are all objects. Well, what is this? Is this, of course, like C prime, right? The radical somehow of this braiding. Okay. So, all right. So now this was sort of like an introduction to the subject. Now, I'll talk about some problems that arise here. The first problem, I'll talk about braided correspondences and minimal extensions. So here are the problem that I can say loosely. See, I try to explain why non-degenerate categories are so preferable compared to others. So we can ask this question. So given a possibly degenerate braided category, category C, can we embed it into a non-degenerate category? And the answer, of course, is yes. Why not? So what we can do, we can take the center of this category, and C being braided is embedded into its own center. Now, this is somehow what makes this theory different, like from usual algebra, right? We used to the fact that the center of a ring is a subring of a ring. So here it's other way around. You see, like for instance, yeah. So if you have like Greenfield center of a Hopf algebra, then it contains Hopf algebra and its dual. So it's actually larger than the original. Yeah, this is good, and it's very useful, okay, because it allows somehow to reduce the study of all tensor categories to that of braided ones, and that's extremely helpful. Again? Yeah, that's right, because, well, you see, yeah, that's exactly the case, yes. Because the same Z can have many gammas, attached to it. Or some will have none, but many will have seven. it's not like quite like that, but what is true is that it's called double for a reason, right? So the Greenfield double of a Hopf algebra, as an algebra, it's H tensor, H star opposite. So that, you know, it's kind of like, dual. Yeah, dual algebra. Well, I don't quite remember, but I mean, there are various ways to do it. Maybe it's co-opposite, but that's the thing, okay? It's actually bigger than H. What? Okay? That's right, yes. So when I say subcategory, I mean like full monoidal subcategory. Okay, did we settle that? All right, so the answer to my question is yes. However, that's not exactly what we are looking for. So what I would rather do, I'll continue here a question. So to a non-degenerate one, of minimal possible dimension. Okay, so I did not touch the dimension theory, but and let me not to do so. But you can imagine that, you know, in case when your category comes like from some algebraic object, the dimension coincides with the usual space dimension. Like for quantum groups, however, that would be like a quantum dimension, so it's not necessarily an integer. But in any case, it's a certain positive number that measures somehow the size of the category. Okay. Objects and the category. So for instance, if you have a semi-simple category and you take dimensions of its objects and take the sum of their squares, that would be the dimension of the category. Just like in, you know, the sum of squared degrees of representations, of reducible representations of a group gives you the order of the group. So by dimension, so let me write this down. Yeah, for finite, yeah. Let's say, okay, yeah. Let's say now we switch to finite category. So dimension of C, a finite. So would be the dimension of squares of the simple objects. Okay. Now, so what I mean of minimal possible dimension. Now, again, if you think about this quadratic forms in the associated linear algebra, then the dimension of the orthogonal complement is determined by the dimension of the space to which you take the complement of, right? So here are dimension of, so let's say if C is embedded into D and D is non-degenerate, then from this consideration that I mentioned, dimension of D is bigger or equal than dimension of C times the dimension of its radical of the symmetric center. So this is, again, this is an analog of the radical. Yeah. Again, completely parallel to linear algebra. And so this kind of controls the dimension of D. It cannot be too small, right? So when we say if this inequality becomes equality, we say that D is a minimal extension. Minimal non-degenerate extension. Again, this is more, in my opinion, than algebraic curiosity. Because of the importance of a non-degenerate categories, we always try to repair the situation. If you have degeneracy, we try to get rid of it. This can be done in many ways. Well, that's one of the possibilities. But it also does lead to an interesting algebra that I'm going to describe next. So one observation is that this is not always possible. Such a minimal extension does not always exist. And it's, of course, interesting to understand why it doesn't exist. Again, this is contrary to our experience with linear algebra. If you like formulate a similar problem about vector spaces and quadratic forms, then there is, of course, such an extension. So we'll try to understand why this is not possible. And to do this, we can actually a little bit generalize this problem that I stated. Okay, so I introduced this notion which extends a little bit this previous setup. So let B1, B2 be a pair of braided categories. I'm sorry, say again. Yeah, well, again, so the dimension of the non-degenerate category containing C is bounded from below by that. So if this bound is achieved, we call it minimal. There is no universal minimal extension. So, there can be several minimal extensions, and they somehow have are equally good. So for example, so again, I wanted to save this for later, but let me say it now for the category of supervector spaces. So which is, of course, one of the simplest imaginable categories. So there are 16 minimal extensions. And this is very celebrated thing in physics. It's called the Kitaev's 16-fold way. So, people who do this topological phases of matter say these things all the time. Okay, so, all right. So let me continue my definition. So let B1, B2 be a pair of braided categories. Then a correspondence between B1 and B2 is a pair of functors. B2 are reversed. Let me explain what that means. So here, where C is braided, the arrows are braided tensor functors. And the images of B1 and B2 centralize each other. So F1, B1 is contained in F2, B2. So reverse here is a sort of like an opposite. So you see, like, if you have a braiding on a category, then what you can do, you can reverse it. So namely, if CXY is braiding, then so is CYX inverse. Again, think about transposition of a bilinear form, right? If B is a bilinear form, then so is its transposed, right? That's exactly what we are doing here. So now, how to think about this? So this correspondence can be taught as a sort of Morita equivalence. Okay, so now let's compare this to the following situation, which is perhaps more familiar. So if you have a pair of categories, let's give them different names, A1, A2 opposite. Now let's suppose they're usual tensor categories. So they're braided, well, on the level of definition, no, not necessarily, okay? Now, if you want to have like invertible correspondence, then yes. But let me compare this like with a kind of more classical situation to make it better understood. So again, you can even think about this situation when A1, A2 are algebras, right? But for me, they will be tensor categories. So A1, A2 are tensor categories. Say again? M is just an abelian category. So now what this represents is a situation when you have a bimodule category over A1 and A2, right? So here are M. This is just a translation. That is, M is an A1, A2 bimodule category. Well, provided, that these two actions somehow centralize each other, right? So that, the left and right actions commute. Now, compare this with this braided situation. You can kind of have similar conditions, only stated in a braided fashion. There is no M. Yes, so, well, you cannot really expect everything literally, That's right, yeah, so, okay. Yeah, so this is kind of like, if you think of this, if you call this a Morita context, then this is kind of the braided Morita context, okay? All right, so now, just like bimodules can be composed, like bimodules can be tensored, so are the correspondences. Now, the correspondence, I thought for a while, what should be appropriate name for it. There is something like this in the theory of von Neumann algebras. It goes back to Alan Kohn. So he considered a pair of von Neumann algebras embedded into type 1, to the algebra of bounded operators on a Hilbert space that centralize each other. And this is, analytically, that's a very complicated notion, but, the idea is pretty much the same, a pair of centralizing algebras living inside something standard, right? So this agrees well with this terminology centralizing that we choose to use. So bimodules can be tensored, and the correspondences, I should really drop quotation marks, but correspondences also can be tensored. Okay, again, let me avoid this kind of explaining the technical side of it. You should take my word for it for now. Okay, like I said, this definition can be done like pretty much for anything. Yeah, I'm about to say this now. I was hoping that I would avoid erasing things on the board, but no. Yes, so. Yeah, that's my understanding of the von Neumann theory, yes. This is more or less the name for it. Hmm? That's right, yeah. That's right. Well, yeah, okay. So for, well, okay, so you can take this as a definition of Morita equivalence if you have kind of like invertible situation like this. Okay, that's more or less the definition. There are characterizations of this in terms of the centers, which I'm going to mention next. So oh, yeah, okay. So now, like I said, once you realize that they can be multiplied, then of course question arises about what are invertible and so on, right? So a correspondence is invertible. Well, first of all, the identity correspondence. One can guess, it should be something canonical. So one can embed B into its center, and so one can embed into the center B reversed, like this. Reversed means like in the sense of this, you take the braiding and replace it by this one. If braiding was symmetric, that would be the original category. If braiding is non-degenerate, that is something very different. Okay, so the identity correspondence and this, and furthermore, so to answer your question is that so a correspondence is invertible if C is non-degenerate and F1, F2 are embeddings. So, I mean, I think you already guessed this before I said this. Now, That's precisely the question I wanted to avoid, but I'll tell you, of course. Now, here we come to the point that I have to erase things. Okay, so let me do it here. So suppose you have a pair of correspondences, let's say between B1 and B2. Embedding means that you have a fully faithful functor. It's kind of like, so you would identify B1 with its image inside C. So suppose you have a pair of this, so between B1 and B2, and between B2 and B3 reverse. So yes, so there is a certain operation. So namely what one does, well, one take the tensor product first. That's not the product yet. But inside this product, there is a canonical algebra I'll put it like this. A lives into B2 reverse tensor B2. And in the semi-simple case, this is just the sum of over the simple objects. This is canonical. In the non-semi-simple case, well, that's a certain integral. Okay, so now, with respect to this algebra, this is in fact, commutative algebra in the sense of braided category theory. And so what one does, one takes certain modules over this commutative algebra. So one take this modules over A in here, and not just all modules, but something which is called local modules. Now, this locality condition, again, let me avoid describing what it is exactly, but the idea is this: so local modules, and this locality condition ensures that resulting category is braided. Okay, because if you just take all the modules, it may fail to be braided. Okay, so that's the idea. You kind of reduce this tensor product by means of a canonical algebra that lives in B2. And of course, at the end of the day, B2 disappears. It's just like B1 and B3 that are left, right? Just when that's how you tensor by modules. Okay, so let me try my skills in erasing this board. I really envy the colleagues who managed to give their talks without, erasing the board. That's my goal, to learn how to do it. Okay, so we were talking about the invertible correspondences. So in particular, there are interesting groups that appear in this way. So, given braided B, one can consider as kind of self-correspondences, right? Or auto-correspondences. So there is a group of its self-correspondences of its like invertible self-correspondences. And yeah, please. Well, you can check that if it's not invertible, then this kind of C splits into a sum of several components, and it fails to be. So there is some computation behind this. This is the best I can tell at the moment. No, correspondence may or may not be invertible, just like a bimodule may or may not be invertible. So this is not definition, it's a characterization. Yeah? If, how about that? I put if and only if. Yeah? Okay, so the group, so in particular, for B symmetric, now in this terminology that I developed here, such a self-correspondence is the same thing as a minimal extension. So this is the group of minimal extensions. Now, you see, a priori, when I gave this definition, it was not clear why minimal extensions of a symmetric category would form a group. So this is something that was introduced by mathematicians and physicists, by Lan, Kong, and Wen, around maybe like 5 or 6 years ago. Now, it also allows you to address this problem. I mentioned that minimal extensions does not always exist. So, B admits a minimal extension if and only if there is a correspondence between B and its asymmetric center. This is invertible correspondence. Does it make sense? In this terminology that I developed. Okay, so now it's about time I introduce like the main heroes of this story, the higher categories. So now, given braided B, there is a notion of a module category. So a B module category is category M along a abelian category along with a bifunctor. Like this, again, satisfying certain things that modules should satisfy, okay? So since you already, I hope you got like the spirit of this theory, you would be able to write the axioms, of this thing. Now, just like modules over commutative ring can be tensored, so are module categories over braided categories. So mod B is a tensor 2 category of B module categories. So why 2 category? Well, because objects are categories, one morphisms are module functors between them, 2 morphisms are natural transformations of this. You have one more level of modules. Now, again, as one would expect, this thing carries a lot information about the original category. And one can go further. So one can take the center, I should be precise here, the 2 center, right? So we are now in the realm of tensor 2 categories, right? So their centers are going to be naturally braided tensor 2 categories, the 2 center of mod B. So called, I'll denote it just like before, Z mod B. And this is a braided tensor 2 category. So this is a rather developed theory by now. Such things can be studied for its own sake, and people do that. But now they are related directly to what we are doing here. So one can, the relation between them is given by the following statement. So I put it here. I to state it. So invertible braided correspondences between like B1 and B2 are on one side, and braided two equivalences of between the corresponding two centers, Z mod B1 and Z mod B2. Okay. So again, what exactly this correspondence? This is, at the very least, is an isomorphism, an equivalence of monoidal groupoids. Well, correspondences can be multiplied, as I just explained, right? Well, but you see, so what I'm saying is that if you have invertible B1, B2 correspondence and invertible B2, B3 correspondence, then you have B1, B3 correspondence, right? Groupoid. Okay. Okay. So, well, think about this analogy. That should hopefully convince you that this is true. If you have modules over a ring, then there is nothing really you can do with them, right? You cannot tensor. But if the ring is commutative, then there is the notion of a tensor product of modules, right? You view a module as a bimodule and tensor them this way. Well, it's not the link tensor product because it's really over B. Okay. The link tensor product, go ahead. No, go ahead, you're the chair. Yeah, so now the link tensor product would just tensor the categories. So here we of course want to take into account that they are not categories but B-modules. So there is like, you can define, the easiest way to define this by universal property and then to show that such thing does exist. Yeah, I think so. Yeah, I kind of implicitly said that we are switching to finite. Yeah. Yeah, otherwise there would be all kind of difficulties which I'm not ready to handle yet. Okay, so yes, so like such things are, so there is an equivalence of this monoidal groupoids. Now, this should not really come as a surprise because there are the centers, if you know, the point I was trying to advocate is that this is sort of a Morita equivalence in the braided setting, right? But if you go back like to the ordinary Morita equivalence, then the zero-dimensional version, that if you have a pair of algebras, so A1, A2, like algebras, and they are Morita equivalent, then of course their centers are isomorphic. That's a classical result in algebra. Well, one-dimensional categorical version. And this is, I think I said something like this, or maybe I didn't. So one-dimensional version of it would be the following. So if, so in my notation, curly A stands for a category and the kind of, the normal A stands for an algebra. So if A1, A2, yeah, Morita, Morita equivalent tensor categories, finite, then the criterion, this is equivalent to the braided equivalence of their Greenfield Center. So there is invertible bimodule between them. That's right. Yeah. Then their Greenfield centers, ZA1, ZA2, are equivalent as braided equivalent. So, totally in the spirit of classical algebra, the center is a complete invariant of a Morita equivalence class. That's one more proof why, you know, the centers are so important. So this is totally in the same spirit, right? So here, however, you know, what's surprising is that to address this rather innocent one categorical problem, we have to, the most natural way to characterize this is to go to the braided monoidal two categories, okay, and have the condition on their centers. I'm sorry, can you say again? You forget two morphisms where? Well, you'll get some truncation of the category, right? But is the question, would you recover this B or what? If you, you do, yes. Yeah. Yeah. In any case, I think this might be the right time to stop. You know, I don't want this braided two categories to stand between people and their lunch. That's not a good way to advertise them. Not trivial. You like take any Greenfield Center, any, for instance, the category of representations of a quantum group. These are R matrices, they're highly non-trivial. And R matrix is precisely what determines the braiding. R matrix is kind of the linear algebra translation of the braiding. So, you know, your category is now a category of representations. Behind every object, there is a vector space. You want to define, you know, isomorphism of such vector spaces. Well, you need an invertible element in the matrix algebra, right? So that's R matrix. If you look at the R matrices associated to quantum groups, they are very non-trivial, as non-trivial as it gets. Well, that's because, you know, what exactly is R matrix? So R matrix is a kind of linear algebra interpretation of the braiding. So you define, like you want a braiding between V tensor W and W tensor V. And now these are representations of a certain Hopf algebra. So they are vector spaces in particular. So what we do, well, we introduce an invertible element R, and we define C. Like again? R lives in the endomorphisms of V tensor W. Okay, so then we define it like on V tensor W by what? So we first permute them, and then we apply R to the result. W tensor, okay, yeah, like this. Yeah, and so then again, braiding is to satisfy certain conditions, right? You know, that is hexagon. But this would translate into Young-Baxter equation for R. Again? Well, for finite groups, they do not really. Well, if you mean just rep G, then, well, there are no very interesting braiding. You can make it, you know, you can, well, unless G is abelian, but, you know, but the most interesting things come, like, for instance, when you take the Greenfield double of G. Then there is, like, an interesting R matrix. And yes. Yeah, absolutely, right. Well, for the most things, no. Certainly not to define like this. Correspondence, I somehow, like, for instance, but for this type of equivalences, you do need. You know, as far as I understand, it wouldn't hold like over real numbers. There are counterexamples. So, but so algebraically closed is needed. Yeah, for characteristic, I would imagine probably not, you know, but I'm not aware of anybody tried to write this carefully. A billion? Well, in the process, you are taking like modules over an algebra, and you want the result to be a tensor category. Galois, like in what, of what? Oh, I don't know if that's relevant to your question, but this is one of the way people kind of like come to this area. There is a Galois theory for von Neumann algebras. It's probably very different from what you meant, but I'm going to say it anyways. So people consider inclusions of Jones von Neumann subfactors. And their symmetries somehow behave, you know, as Galois symmetries. And the right way to describe them is using the tensor categories. That's what I know. I'm sorry, I couldn't hear you well. Well, geometric meaning, it's like vanishing of the radical of a quadratic form. You know, this is kind of a geometric condition.
Okay, that's one of the
you know, it's right. So, like in general, this notion of there is like a geometric intuition. So in this case, like symmetric subcategories, they correspond to coisotropic subspaces. There is a notion of kind of a Lagrangian, you know, subalgebra or subcategory, things like that.
So for example, if C is representation of a certain group, non-degeneracy will mean something for this group, or
well,
no, not at all. It's not. That's not
no,
the correct
For group, as long as group is non-abelian, you cannot really turn representations of G into non-degenerate. So somehow, this you have to really go away from groups and consider more general structures like Hopf algebras.